Right now, light that left a galaxy 13 billion years ago is hitting your eyes. The James Webb Space Telescope just confirmed something impossible. Galaxies exist where they shouldn't, formed when they couldn't, challenging everything we thought we knew about the universe's size and age. In the next 2 hours, we will journey to the edge of observable space 46 billion light-years away. We will witness galaxies racing away faster than light itself, structures spanning billions of light years, and cosmic voids that swallow entire galaxy clusters. If you are ready to see the true scale of reality, like this video and subscribe. We begin. The first image stopped astronomers' cold web pointed at a patch of sky no bigger than a grain of sand held at arm's length. For 12 hours it collected photons. When the data came back, scientists counted galaxies. They expected thousands. What they saw made them recount 3 times. Over 45,000 galaxies packed into that tiny window, each one a complete system spinning through space with hundreds of billions of stars, each one existing in a sliver of sky you would never notice if you looked up tonight. The density defied predictions. Previous models suggested sparse distribution at cosmic distances. JWST confirmed the opposite. Wherever we point, galaxies flood the view. Here is what that number means for you. Take every star visible to your naked eye on the clearest night, maybe 3,000 if you stand far from cities. Now understand that each galaxy in Webb's image contains more stars than you will ever see without a telescope. Multiply those 3,000 visible points of light by billions. That gives you one galaxy. Now multiply that galaxy by 45,000, all in one grain of sand's worth of sky. The mathematics becomes dizzying. If this density holds across the entire celestial sphere, the observable universe contains far more galaxies than earlier estimates suggested. Hubble gave us a number 200 billion galaxies. JWST hints at 2 trillion, possibly more. Every direction we look explodes with structure, but density alone does not tell the full story. These galaxies exist at different distances, different times. Light from the nearest took millions of years to reach the telescope. Light from the farthest traveled over 13 billion years. Webb sees layers of cosmic history stacked in one image like rings in an ancient tree. Each galaxy represents a different epoch, a different chapter in the universe's evolution. The deeper implication terrifies and thrills in equal measure. If 45,000 galaxies hide in one random patch, what exists in the patches we have not examined, Webb cannot look everywhere at once. The telescope must choose targets carefully, balancing science goals against limited observation time. Most of the sky remains unexplored at this resolution. What lurks in those dark corners? The implications stretch beyond mere counting. Galaxy density affects our understanding of dark matter distribution. It influences calculations about cosmic expansion rates. It forces us to reconsider how quickly structure formed after the Big Bang. A universe this crowded with galaxies demands more matter, more gravity, more dark energy to hold it all together while pushing it apart. Scientists expected a cosmic web, filaments of galaxies threading through voids. JWST confirmed the web exists, but the threads are thicker than anyone predicted. The voids between them might be smaller, less empty. Our models assumed vast reaches of nothing punctuated by rare islands of matter. Reality shows something denser, more intricate, more connected. This matters for searching for life beyond Earth. More galaxies mean more stars mean more planets mean more chances for chemistry to stumble into biology. The odds of finding another civilization improve with every galaxy Webb adds to the census. We thought we lived in a universe with hundreds of billions of opportunities. JWST suggests trillions. Yet, here is the twist that keeps astronomers awake. Most of these galaxies are unreachable. The universe expands. Space itself stretches between us and them. Light from the most distant galaxies is already redshifted into infrared. In time, they will fade beyond any telescope's ability to detect. We see them now only because we built Webb at exactly the right moment in cosmic history. Miss this window and future civilizations might never know these galaxies existed. The first deep field image revealed more than density. It revealed urgency. The universe is showing us its full scale right now, today, before expansion carries too much of it beyond our horizon. What we discover in the next decade might be our last chance to witness the complete cosmic inventory, and we have only examined one grain of sand. JADES G140 should not exist. Webb found it in the same deep field. A smudge of ancient light older than anything Hubble ever confirmed. Spectroscopy revealed its secret. Light from this galaxy began traveling toward us 13,400 million years ago. It formed just 290 million years after the Big Bang. That time frame breaks our models. Early universe conditions were supposed to be too chaotic for galaxy formation. Hydrogen and helium dominated everything, still cooling from the initial explosion. Stars had barely begun to ignite. Dark matter had only started clumping together, pulling ordinary matter into gravitational wells. Galaxies should have taken longer, needed more time to organize. JADES did not wait. The galaxy spans 1,600 light-years across, compact compared to modern spirals. But within that small volume, stars already burned. Not just a handful of protostars, but enough stellar furnaces to make the galaxy visible across 93% of cosmic history. The light we detect now is faint, redshifted into wavelengths Hubble could not see. Webb's infrared sensors caught what no previous instrument could. Here is why this discovery matters. Every cosmological model depends on assumptions about when structure formed. Computer simulations start with conditions, moments after the Big Bang, then run forward in time. They predict when first stars should appear, when those stars should cluster into galaxies, when galaxies should merge into larger systems. JADES formed earlier than any simulation suggested possible. Either our simulations are wrong or something sped up galaxy formation. One theory proposes dark matter concentrated faster than expected. If dark matter clumped into dense halos earlier, ordinary matter could follow, pulled by gravity into collapsing clouds that ignited stars. Another theory suggests the first stars were far more massive than we calculated, burning brighter and dying faster, enriching their surroundings with heavy elements that enabled rapid galaxy growth. Both theories remain unproven. What scientists know for certain, this galaxy exists. Spectroscopic data confirms its distance. The red shift measurement is solid, verified multiple times by different teams. You cannot fake a red shift. Light does not lie about how far it traveled or how much space expanded during its journey. The galaxy's chemical composition adds another mystery. Oxygen appears in the spectrum. Elements forged inside stars and expelled when those stars died. But how many stellar generations does oxygen require? First stars contained only hydrogen and helium from the Big Bang. When they exploded, they scattered heavier elements. Second-generation stars incorporated those elements, created more, died, and scattered them again. Third-generation stars inherited an even richer chemical mix. JADES shows oxygen just 290 million years after creation. The timeline feels compressed, rushed. Stellar evolution operates on schedules we thought we understood. Massive stars live only millions of years before going supernova. Medium stars like our own last billions of years. To see oxygen this early, multiple generations of massive stars must have lived and died in rapid succession. The galaxy needed time to build. Stars needed time to burn. Supernova needed time to scatter their elements. 290 million years seems impossible. Yet there it sits, frozen in Webb's data, defying comfortable assumptions. Astronomers call it a tension between observation and theory. When reality contradicts your model, reality wins. The model must change. Finding JADES also raises an uncomfortable question. If Webb detected one impossibly early galaxy in a small survey patch, how many more exist beyond our current search areas? The telescope cannot examine the entire sky at this sensitivity. It must prioritize targets, spending hours or days on single fields. Most of the universe remains unexplored at the depth required to spot these faint, distant objects. Each new deep field might reveal more cosmic rule breakers. The implications ripple outward. If galaxies formed faster than predicted, the entire timeline of cosmic evolution shifts earlier. Ionization, the period when first stars ionized hydrogen throughout space, might have happened sooner. The cosmic dark ages, the gap between the Big Bang and first light, might have been shorter. Everything we thought we knew about the universe's childhood is changing, and JADESGS Z140 is just the beginning. Imagine watching something that already finished billions of years before Earth formed. That is what happens every time Webb images a distant galaxy. The light entering the telescope left its source when the universe was young, then crossed space for eons. It traveled through expanding cosmos, through clouds of gas, past billions of other galaxies, until finally reaching our instruments. Light moves at 186,000 ms. Nothing goes faster. That speed limit defines how we experience the universe. When you see lightning, you watch photons that left the bolt milliseconds ago. When you see the moon, you watch light from 1 second in the past. When you see our closest stellar neighbor, you watch light from over 4 years ago. Scale that up to cosmic distances. The Andromeda Galaxy sits 212 million light-years away. Every photon from Andromeda began its journey toward Earth when our ancestors were barely learning to walk upright. The light shows us Andromeda as it was, not as it is. If that galaxy exploded yesterday, we would not know for another 212 million years. JWST looks farther still. The telescope detects galaxies whose light traveled 13 billion years or more. When those photons started their journey, Earth did not exist. Our solar system did not exist. The Milky Way was still assembling from smaller proto-galaxies. Dinosaurs would not appear for another 12 billion years. Understanding this changes everything about measuring the universe. Astronomers do not measure distance directly. They measure time. When we say a galaxy is 13 billion light-years away, we mean light from that galaxy took 13 billion years to reach us. But here is the complication. Space expanded during that journey. The galaxy moved while light traveled. Imagine running on a treadmill that constantly speeds up. You run forward at steady pace, but the treadmill pulls the finish line farther away faster than you approach it. Light faces the same problem. As photons cross space, space itself stretches, carrying distant galaxies farther from us. This means the galaxy Webb sees is not where it was. When light left Jade's 13,400 million years ago, that galaxy was much closer, maybe 3 billion light-years away. But during the journey of its light toward us, space expanded. The galaxy receded, carried by cosmic expansion. By now that galaxy sits over 30 billion light-years distant. We see its past position, not its present location. This creates a strange disconnect between observation and reality. Every distant object Webb images exists simultaneously in two places, where we see it and where it actually is. Now we can calculate the current position using expansion rates, but we can never observe it. Light from the galaxy's current state has not reached us yet. It will arrive billions of years from now. The travel time also affects how we understand galaxy evolution. We see Jade as it was 290 million years after the Big Bang, but that galaxy kept evolving after light left. It might have merged with neighbors, it might have grown into a massive elliptical, it might have died. Stars exhausted, gas depleted. We will never know what happened next. The light from 1 billion years later is still in transit, crossing space at its steady pace. Light from 2 billion years later has not reached halfway. Every subsequent chapter in that galaxy's story remains hidden, encoded in photons that have not yet completed their journey. This is the price of looking deep into space. We see history, not the present. We see beginnings, not endings. We watch the universe's childhood while the universe has already grown into something unrecognizable. The galaxies we study might not even exist anymore in any form we would recognize. But here is what keeps astronomers searching. Even though we see the past, that past is real. Those galaxies existed, those stars burned, those atoms assembled into complex structures. By studying light from different distances, different eras, we piece together the universe's biography. We see infant galaxies at 13 billion years ago, adolescent galaxies at 8 billion years ago, mature galaxies at 3 billion years ago. We watch the universe grow up, and every photon that crosses space carries information we cannot get any other way. The numbers sound impossible at first. If light traveled for 13 billion years to reach us, the galaxy should be 13 billion light-years away. Simple mathematics, except space does not hold still while light travels. Space expands, stretches, grows larger with every passing moment. That expansion changes everything about distance. When light left the most distant galaxies Webb observes, space was smaller, much smaller. The universe was perhaps 1/10 its current size. Galaxies sat closer together. The distance light needed to cross was shorter, but as those photons traveled toward us, space expanded beneath them. Think of an ant walking across a stretching rubber band. The ant moves forward at steady speed, but someone keeps pulling the rubber band longer. The ant advances, but the far end of the band recedes faster than the ant walks. By the time the ant reaches the end, the band has stretched far beyond its original length. Light experiences this same phenomenon. Photons from distant galaxies move toward us at light speed, never slowing, never stopping. But space expands while they travel. The expansion does not slow the photons down. Instead, it increases the total distance they must cover. By the time those photons reach Webb's mirrors, the galaxy they left has moved much farther away. Current calculations place the most distant confirmed galaxies at over 30 billion light-year from Earth right now. Not 13 billion, 30 billion. That galaxy we see from 13 billion years ago, it currently sits 30 billion light-years away because space expanded during the light's journey. If we could freeze time and measure the distance directly, we would need to cross 30 billion light-year of space to reach that galaxy's present location. This creates the observable universe's true scale. We can see in every direction roughly 13 billion 800 million light-year back in time. That is the age of the universe, the maximum time light has had to travel. But those galaxies we see at the edge have all moved farther away due to expansion. Looking in all directions, the observable universe spans roughly 93 billion light-year across, 93 billion light-year from edge to edge. Earth sits near the center of our observable bubble, not because we are special, but because observation defines the sphere. Any observer anywhere in the universe sees themselves at the center of their own observable region. Each location has its own cosmic horizon, its own sphere of visibility. But here is what disturbs comfortable thinking. The 93 billion light-year sphere represents only what we can see. The actual universe extends beyond that. How far beyond? Nobody knows. It might be infinite. Current measurements suggest space is flat, which typically implies infinite extent. If true, the universe has no edge, no boundary, no center. What we observe is a bubble of visibility inside something vastly larger. Imagine standing in a thick fog. You can see perhaps 100 ft in any direction. That creates your visible sphere 200 ft across. But the forest extends miles beyond the fog. You just cannot see it. The fog limits your observation, not the forest size. Cosmic expansion creates a similar limit. Beyond a certain distance, galaxies recede faster than light can cross the expanding space between us. Their light will never reach us, no matter how long we wait. Those regions exist, contain galaxies, stars, planets, but they remain forever beyond our cosmic horizon. JWST sees nearly to that horizon. The telescope detects galaxies from when the universe was just a few 100 million years old. Much earlier than that, the universe was too hot and dense for light to travel freely. Photons scattered off free electrons in a thick plasma. No galaxy images exist from before that era because photons could not escape. That earliest visible moment defines our ultimate look-back limit. We can observe the cosmic microwave background from 380,000 years after the Big Bang. Before that, the universe was opaque. Anything that happened in the first 380,000 years remains hidden behind an impenetrable wall of plasma. What JWST revealed is this: the visible universe is enormous, beyond human comprehension, spanning 93 billion light-years. Yet, even that unimaginable scale might represent only a tiny fraction of what actually exists. Most of reality hides beyond our cosmic horizon. We see a bubble. The universe is possibly infinite, and we have no way to observe what lies outside our sphere. After the Big Bang came expansion, cooling, the formation of first atoms, then nothing. Hundreds of millions of years passed in near total blackness. No stars burned, no galaxies shone, just hydrogen and helium drifting through expanding space, gradually pulled together by dark matter's invisible gravity. Scientists called this period the cosmic dark ages. Calculations suggested the darkness lasted until perhaps 600 million years after creation. Then first stars would ignite, galaxies would form, light would return to the cosmos. JWST aimed at this era, expecting to find the universe just beginning to wake up. Instead, it found galaxies already assembled. Spectroscopic analysis confirmed structures formed as early as 200 million years after the Big Bang. By 500 million years, fully formed galaxies filled space. These were not scattered protostars or loose collections of gas. They were organized systems with rotation, structure, defined shapes. The speed of assembly shocked researchers. Galaxy formation requires multiple steps, each taking time. Dark matter must clump into halos. Ordinary matter must fall into those halos. Gas must collapse, heat up, cool down. Molecular clouds must fragment. Stars must ignite. Those stars must create heavy elements. New generations must form from enriched material. Each step was supposed to require millions of years. Yet here were galaxies complete in just 500 million years total. The timeline compressed impossibly. Computer simulations could not reproduce this rapid formation without changing fundamental assumptions about physics, dark matter behavior, or initial conditions. One explanation suggests dark matter concentrated faster than models predicted. If dark matter halos formed earlier and denser, they could pull ordinary matter together more quickly. Stronger gravity means faster collapse. Faster collapse means quicker star formation. But this requires adjusting how we understand dark matter's properties, making it clump more efficiently than current theories allow. Another possibility involves the first stars themselves. Population 3 stars, the initial generation, might have been far more massive than calculated. If these stellar giants burned hundreds of times brighter than modern stars, they could have ionized surrounding gas more effectively. Their deaths as supernovae would scatter heavy elements faster. This could accelerate subsequent generations of star formation. Both ideas remain hypothetical. What cannot be disputed? The galaxies exist. Webb's data is clear. Spectra show red shifts corresponding to 500 million years after the Big Bang. Morphology shows organized structure. Chemical analysis shows evolved stellar populations. These discoveries force a confrontation with comfortable assumptions. Standard cosmology depicts a leisurely progression from chaos to order. The Big Bang explodes. Space expands and cools. First atoms form at 380,000 years. Dark ages last until 600 million years. First stars ignite. Galaxies slowly assemble over the next several billion years. JWST suggests a different story. The universe organized faster than expected. Within 500 million years of creation, galaxies already dominated. The cosmic dark ages were shorter, the dawn brighter and more sudden. Instead of gradual awakening, the universe experienced rapid transformation from darkness to light. This matters for understanding everything that came after. If galaxies formed quickly, they had more time to evolve, merge, grow. The structures we see today might have deeper histories than we suspected. Galaxy clusters could be older. Superclusters could have assembled earlier. The cosmic web could have matured faster. The implications extend to reionization. This period, when stellar radiation ionized hydrogen throughout space, supposedly lasted hundreds of millions of years. If galaxies formed earlier and more abundantly, reionization could have completed faster. The universe might have cleared its fog of neutral hydrogen sooner than models suggest. Every adjustment cascades through cosmic timelines. Change when galaxies form, and you change when galaxy clusters form. Change cluster formation, and you change when superclusters emerge. Change supercluster emergence, and you change how the cosmic web evolved. Each discovery from JWST pulls on threads that unravel entire tapestries of cosmological understanding. Yet despite these challenges, astronomers feel excitement rather than frustration. Wrong models can be fixed. Incorrect assumptions can be revised. What matters is matching theory to observation, not defending outdated ideas. JWST provides observations. Scientists must now build better theories that explain rapid galaxy formation while maintaining consistency with other established facts. The work continues, accelerated by each new deep field image. But one question haunts every meeting, every paper, every discussion. If galaxies formed this quickly, 500 million years after the Big Bang, what happened even earlier that we have not detected yet? The shapes made astronomers double-check their instruments. Webb revealed not just early galaxies, but mature ones, spiral arms, central bulges, defined structures. These features supposedly required billions of years to develop. Yet there they sat, already formed less than 1 billion years after creation. Spiral galaxies are delicate structures. Arms wind through disks of stars and gas shaped by density waves and gravitational interactions. Building this requires time for rotation to organize matter, for dark matter halos to stabilize, for stellar feedback to regulate star formation. Current models suggested spirals did not appear until at least 3 billion years after the Big Bang. JWST found spirals at 700 million years. The images left no room for interpretation. Clear spiral structure, multiple arms, central concentration. These were not irregular blobs of stars slowly organizing. They were already mature systems with rotation curves, organized stellar populations, distinct morphology. Elliptical galaxies raised similar questions. These massive, smooth systems form through galaxy merges. Two or more spirals collide, their collisions ejecting gas and leaving behind a ball of stars. The process is violent, chaotic, requiring multiple merger events to build large ellipticals. Scientists expected ellipticals to appear late in cosmic history after billions of years of galaxy interactions. Webb found massive elliptical already assembled before the universe was 1 billion years old. The size posed its own mystery. Some of these early ellipticals contained stellar masses equivalent to 100 billion stars, similar to our own. Where did all that matter come from? How did it concentrate so quickly? Gas clouds in the early universe were hot, turbulent, difficult to collapse into dense stellar factories. Yet collapse they did. Chemical composition added another layer of strangeness. Mature galaxies show chemical enrichment, heavy elements created by multiple stellar generations. The spectra from these early mature galaxies revealed oxygen, carbon, nitrogen, elements that require stars to live and die, spreading their processed material. This demands time. Massive stars live only a few million years before exploding. Medium stars last billions of years. To achieve the chemical enrichment Webb detected, several generations of massive stars must have cycled through birth, life, death. That should have taken hundreds of millions of years minimum. These galaxies accomplished it faster. One controversial explanation suggests the first stars were far stranger than modern ones. If population 3 stars burned at extreme masses, perhaps hundreds of times larger than anything we see today, they could have lived and died in just thousands of years. Thousands, not millions. Rapid cycling would scatter elements quickly, but this requires stellar physics unlike anything observed. No confirmed population 3 star has ever been directly detected. We infer their existence from chemical signatures in ancient gas clouds. Making them massive enough to explain JWST's observations pushes them into speculative territory. Another idea proposes accelerated star formation. If early galaxies converted gas into stars far more efficiently than modern galaxies, they could build large stellar populations quickly. Modern galaxies convert only a small percentage of available gas into stars. Maybe early galaxies operated differently, turning 50% or more of their gas into stars in rapid bursts. Both theories face challenges. Star formation too efficient creates different problems. It would deplete gas reserves quickly, shutting down future star formation. Yet many of these early mature galaxies show ongoing star formation, suggesting they retained gas despite earlier bursts. The balance proves tricky to model. The mature morphologies also suggest stable conditions. Spiral arms do not persist in chaotic environments. They get disrupted by mergers, torn apart by gravitational interactions. Their presence indicates the galaxy has settled, found equilibrium, stopped experiencing major disturbances. That stability supposedly required billions of years in a crowded early universe where galaxies constantly collided. Somehow these systems found calm in the chaos. What disturbs cosmologists most is not one mature galaxy appearing early. It is the abundance. JWST deep fields reveal dozens of mature systems in small patches of sky. If this density holds across the entire universe, mature galaxies dominated within the first billion years. The universe skipped childhood and jumped straight into adolescence. This accelerated maturity affects predictions about galaxy evolution. If maturity came early, what happened during the next 12 billion years? Did these galaxies continue evolving, or did they plateau? Modern galaxies show diverse properties, but maybe that diversity was already established early and simply persisted. We thought galaxy evolution was progressive, developmental. JWST suggests it might have been rapid and early with less subsequent change than assumed. The universe assembled its structures quickly, then spent billions of years in relatively stable configurations. If true, this reshapes our entire narrative of cosmic development, and it makes the next question unavoidable. What physical processes operated in the early universe that no longer function today? Space is not randomly filled with galaxies. They organize into structures, vast patterns threading through the void. Astronomers call this the cosmic web, filaments of galaxies connected by gravity surrounding enormous empty regions. Hubble revealed hints of this web structure. JWST confirmed it extends far deeper into cosmic history than anyone mapped before. The web began forming early. At just 2 billion years after the Big Bang, JWST detected filamentary structures stretching across tens of millions of light years. Galaxies lined up along invisible threads of dark matter, creating a pattern that resembles neural networks or fungal mycelium. The similarity is not coincidence. Gravity follows mathematical rules that create similar structures across scales. Dark matter clumped first, forming the skeleton. Ordinary matter followed, pulled into the gravitational wells created by dark matter concentrations. Where filaments intersect, matter piles up densely. These intersections become galaxy clusters, the nodes of the cosmic web. Between filaments lie voids, enormous regions of space where few galaxies exist, where matter was pulled away toward denser regions. The voids are not completely empty, but contain far fewer galaxies than average. Some voids stretch across hundreds of millions of light years, vast bubbles in the cosmic foam. JWST traced individual filaments across previously invisible distances. One structure spans over 300 million light-year, connecting multiple galaxy clusters in a continuous chain. The filament contains thousands of galaxies, all moving under the influence of collective gravity. Gas streams along these filaments, funneling material from low-density regions toward high-density nodes. This flow feeds galaxy growth. Galaxies at filament nodes receive constant infall of fresh gas, fuel for ongoing star formation. Isolated galaxies far from filaments exhaust their gas reserves and go quiet. The cosmic web does not just organize galaxies spatially, it determines which galaxies thrive and which starve. Previous surveys mapped the local cosmic web within a few billion light-year. JWST extended the map to 10 billion light-year, showing the web existed and functioned much earlier than expected. This early establishment means the large-scale structure of the universe was set quickly, perhaps within the first 2 billion years after creation. Once established, the pattern persisted. Filaments grew thicker as more galaxies fell into them. Voids grew larger as expansion pushed them apart, but the basic topology remained consistent. The web we see today is the same web that formed billions of years ago, grown and expanded but fundamentally unchanged. This stability has implications for dark matter. If the web formed early and persisted, dark matter's distribution must have been stable. Dark matter cannot evaporate or disperse easily. It concentrates in filaments and clusters, holding the structure together despite cosmic expansion. Without dark matter, the web would dissolve as expansion pulls galaxies apart. The web also influences galaxy properties in unexpected ways. Galaxies along filaments tend to be spiral, actively forming stars. Galaxies at cluster nodes tend to be elliptical, older, quieter. Environment shapes evolution. Your location in the cosmic web determines your future. JWST revealed something else strange about the web. Some filaments appear thicker, denser than cosmological simulations predicted. If simulations are accurate, this suggests additional matter exists in filaments that we have not detected. The missing mass might be dark matter, or it might be ordinary matter in forms too faint to see directly. Warm gas filling the space between galaxies could account for some of this. This intergalactic medium glows faintly in X-rays, visible only with specialized instruments. JWST cannot detect it directly, but the gravitational effects suggest its presence. If confirmed, this gas represents a significant fraction of the universe's ordinary matter previously uncounted. The cosmic web also sets the stage for everything that follows. Galaxy collisions happen when filaments intersect. Supercluster formation occurs at major nodes. The distribution of matter at the largest scales determines where structure concentrates. Understanding the web means understanding the framework within which all cosmic evolution occurs. Yet the web itself poses mysteries. Why did it form this particular pattern? Initial conditions after the Big Bang were nearly uniform. Tiny fluctuations in density that later grew into structure. But how did those tiny quantum fluctuations during inflation create a web pattern billions of light years across? The connection between quantum and cosmic scales remains poorly understood. Inflation theory suggests quantum uncertainty during the universe's first fraction of a second got stretched to cosmic size. Those stretched uncertainties became density variations. Gravity amplified the variations into the web. But the precise mechanism linking quantum foam to galactic filaments involves physics we cannot test experimentally. JWST cannot answer that question directly. But by mapping the web across cosmic time, it provides data that theorists use to test inflation models. The web structure constrains what could have happened during inflation. Too much variation or too little, both cause problems. What we observe must match what inflation predicts, and increasingly small mismatches appear between observation and prediction. El Gordo hangs in space like a cosmic monument to gravity's power. This galaxy cluster sits 7 billion light-year away, the most massive cluster ever detected at that distance. Mass equivalent to 3 quadrillion times our own stellar home crushes together into a relatively small region. The gravity is so intense it bends space, creating gravitational lensing visible in every Webb image of the structure. But El Gordo is not alone. It sits within a larger structure, a supercluster that extends over 1 billion light-year. Superclusters are collections of galaxy clusters, the largest gravitationally bound structures in the universe. They represent the ultimate scale of cosmic organization, 1 billion light-year. Travel at light speed, and you would need 1 billion years to cross it. The entire history of complex life on Earth, from first cells to humans, spans less time than crossing this single structure. Every species that ever lived, every ocean that ever formed, every mountain that ever rose, all of it happened in less time than light needs to traverse this supercluster. Yet El Gordo's supercluster is not even the largest. The Lanaya supercluster, which contains our Milky Way, extends 520 million light-years across. The Shapley supercluster measures 650 million light-year. The Hercules Corona Borealis Great Wall spans 10 billion light-year, though its status as a single-bound structure remains debated. These structures challenge our understanding of cosmic formation timelines. Building something a billion light-year across requires gravity to pull matter together across vast distances. But cosmic expansion fights against gravity. Space grows larger, pushing structures apart. For a supercluster to form, gravity must overcome expansion, concentrating matter despite the universe pulling everything apart. This takes time. Current models suggest superclusters need at least 8 billion years to assemble. Matter must flow from surrounding regions toward the densest spots. Galaxy clusters form first. Then those clusters gradually attract each other, creating larger associations. Yet El Gordo already existed 7 billion years ago. Light from El Gordo took 7 billion years to reach us. When that light left, the universe was only about 6,400 million years old. By that time, El Gordo had already assembled into a massive cluster and joined a supercluster structure spanning a billion light-year. The formation timeline feels compressed again. From the Big Bang to El Gordo's existence required less than 7 billion years. That is half the universe's current age. Somehow, gravity organized matter into billion light-year structures in just half the time available. El Gordo itself shows signs of ongoing assembly. The cluster is actually 2 massive clusters colliding at several million miles an hour. The collision generates shock waves, heating gas to hundreds of millions of degrees. X-ray observations reveal the hot gas glowing intensely. The collision will eventually merge both clusters into one even more massive structure. This process takes billions of years. The clusters approach, interpenetrate, separate, return, merge. Gas collides and heats. Galaxies pass through each other, mostly untouched because stars are so far apart. Dark matter halos overlap, combining gravitational influence. Eventually, everything settles into a new equilibrium. We see one moment in this long dance. The collision happened billions of years ago, when light left. By now, 7 billion years later, the merger has progressed much farther. We cannot see the current state. We watch ancient history unfold, observing a process that might have already completed. What makes El Gordo's supercluster significant is its mere existence. Structures this large should be rare, edge cases in the cosmic distribution of matter. Finding them at high red shift when the universe was younger suggests they were more common than models predicted. Either structure formed faster than we calculated, or our statistics about large-scale organization need revision. JWST's deep fields help resolve this question. By mapping distant superclusters and comparing their abundance to nearby ones, Astronomers track how these structures evolved over time. If distant superclusters are rare, it confirms current models. If they are common, models need adjustment. Early results suggest they are not as rare as expected. Several distant superclusters have been identified, hinting at an earlier epoch of large-scale structure formation. The universe organized itself quickly at multiple scales simultaneously. Small galaxies, massive clusters, enormous superclusters all emerged in a compressed time frame. This coordinated formation points toward initial conditions. The Big Bang did not create a perfectly smooth universe. Quantum fluctuations during inflation seeded tiny density variations. Those variations existed at all scales, from galaxy-sized to supercluster-sized. When gravity started amplifying them, all scales grew simultaneously. Superclusters did not wait for galaxies to form first, they all formed together, a hierarchy of structure emerging in parallel. This means the cosmic web pattern was imprinted very early, determined by those initial quantum seeds stretched to cosmic size during inflation. What we see now is the mature result of processes that began in the first fraction of a second after creation, and every supercluster carries information about those earliest moments frozen in its structure. 650 million light-years away, something massive warps the fabric of space. The Shapley concentration contains over 20 galaxy clusters, each cluster holding thousands of galaxies. Combined mass reaches levels that strain description. Gravity from this concentration influences motion across 500 million light-years of space, including our motion. The Milky Way moves through space at over 1 million mph. Part of that motion comes from the Big Bang's initial expansion. Part comes from local gravitational influences, but a significant component comes from the Shapley concentration pulling us toward it. We are falling toward Shapley. So is the entire local group, our collection of nearby galaxies, including Andromeda. So is the Virgo cluster, a larger group of galaxies we orbit around. Everything within several hundred million light-year feels Shapley's pull, like water spiraling toward a drain. The implications disturb comfortable assumptions about cosmic motion. We thought the universe expanded uniformly, all galaxies moving away from each other in accordance with Hubble's law. That remains generally true at large scales, but at scales of hundreds of millions of light-years, local concentrations create additional motions. Astronomers call this peculiar velocity. It is motion independent of expansion, caused by gravitational attraction toward nearby massive structures. Peculiar velocities complicate measurements of cosmic expansion because you must separate expansion motion from gravitational motion to get accurate numbers. Shapley's influence means our measurements of expansion have built-in uncertainty. When we observe distant galaxies, we measure their redshift, then calculate how fast space expands between us. But our motion toward Shapley adds to our velocity, changing the observed redshift slightly. Correct for this, and expansion rates shift. Small corrections cascade into larger uncertainties. The Hubble tension, the disagreement between different measurements of expansion rate, might partially result from peculiar velocities we have not fully accounted for. If Shapley pulls us faster than calculated, or if other massive structures create motions we have not detected, our expansion measurements could be systematically wrong. This matters for measuring dark energy. Dark energy strength determines how fast the universe expands. To measure dark energy, we measure expansion. If our expansion measurements include errors from peculiar velocities, our dark energy calculations inherit those errors. Small mistakes about Shapley's influence propagate through every cosmological parameter. But Shapley's pull affects more than just measurements. It represents something deeper about cosmic structure. Concentrations this massive should be rare in a universe where expansion wins over gravity. Shapley exists because matter concentrated unusually densely in that region, overcoming expansion's tendency to spread everything apart. Why did matter concentrate there? Trace Shapley's history backward. Billions of years ago, that region contained higher than average density. Gravity pulled more matter in, increasing density further. This positive feedback created runaway concentration, snowballing into the massive structure we see today. But what caused the initial higher density? Quantum fluctuations during inflation seeded variations. Some regions got slightly more matter, others slightly less. Those small differences, amplified by billions of years of gravity, became Shapley and other large-scale structures. Every supercluster traces back to quantum uncertainty in the first moments of existence. Shapley's future is also interesting. As the universe expands, distant regions accelerate away. Eventually, even Shapley's gravity cannot pull against accelerating expansion. Galaxies currently falling toward Shapley will slow, stop, reverse direction. Expansion will win, carrying everything apart despite gravity's pull. This transition has not happened yet. For now, Shapley still pulls. Billions of years from now, that pull will weaken as expansion dominates. Shapley will become isolated, surrounded by an expanding void as other structures accelerate beyond its gravitational reach. But we will never see that future. Billions of years from now, our own stellar home will be gone, absorbed into Andromeda during their inevitable collision. The combined galaxy will likely fall into the Virgo cluster, merging with other local galaxies. That larger system might eventually join Shapley, or it might be carried away by expansion first. The outcome depends on timing we cannot precisely calculate. What JWST revealed about Shapley comes from mapping its extent more accurately. Previous surveys estimated its mass and distance. Webb's deep imaging detected faint galaxies on Shapley's periphery, defining its boundaries more precisely. The structure is larger and more massive than earlier estimates. This means its gravitational influence extends farther. Our peculiar velocity toward it might be greater. The corrections needed for expansion measurements might be larger. Every parameter affected by Shapley needs revision, and Shapley is just one concentration among many that influence local motion. Einstein predicted it almost a century ago. Mass bends space. Light follows that bent space. Massive objects act as lenses, magnifying and distorting light from objects behind them. For decades, this remained theoretical. Then astronomers found real examples. And now JWST uses gravitational lensing as its most powerful tool. Here is how it works. A massive galaxy cluster sits between Earth and a distant galaxy. The cluster's gravity warps space around it. Light from the background galaxy travels through that warped space, following curved paths. The paths converge toward us, concentrating light that would otherwise spread out and become invisible. The result is magnification. The background galaxy appears brighter and larger than it would without the lens. Sometimes magnification reaches factors of 10, 20, even 50 times. Objects too faint to detect become visible. Details too small to resolve become clear. JWST exploits this constantly. The telescope targets known massive clusters specifically to use them as natural magnifiers. The clusters themselves are interesting, but what lies behind them is revolutionary. Entire populations of distant galaxies become accessible only through lensing. One image from Webb shows this dramatically. The cluster MAX J416 produces hundreds of lensed images. Background galaxies appear multiple times, stretched into arcs, smeared into streaks, distorted into strange shapes. Each arc is one distant galaxy magnified and warped by the cluster's gravity. The distortion reveals the lens's mass distribution. By mapping where light bends and by how much, astronomers reconstruct the cluster's total mass, including dark matter. Most of the lensing comes from dark matter, invisible but massive. Its gravity dominates the bending. This makes lensing one of the few ways to map dark matter directly. You cannot see dark matter, you can only infer it from gravitational effects. Lensing provides those effects in precise, measurable form. The more bending, the more mass. Strong lensing produces multiple images. Weak lensing creates subtle stretching. Both reveal dark matter's presence. But lensing does more than map mass. It magnifies the faintest, most distant galaxies beyond what any telescope could detect alone. Some galaxies visible in lensed fields would require a telescope hundreds of feet across to see directly. Lensing provides that magnification for free, using gravity itself as an enormous lens. The trade-off is distortion. Lensed galaxies appear stretched, duplicated, warped. Reconstructing their true shape requires computer modeling. Astronomers measure how light bent, calculate the lens's properties, then reverse the distortion to see what the galaxy actually looks like. Sometimes one galaxy creates dozens of images. A particularly massive cluster can produce 5, 10, even 20 separate images of the same background galaxy. Each image shows the galaxy from a slightly different light path bent around different parts of the cluster. The images appear scattered across the sky, connected only by careful analysis. Finding all images from one source is detective work. Spectra help identify matches. If two arcs have identical redshift and chemical composition, they likely come from the same galaxy. Position on the sky also matters. Lensing models predict where images should appear. Finding arcs in predicted positions confirms the lens reconstruction. Webb discovered something unexpected about lensing. Some of the most distant galaxies only appear in lensed fields. Without magnification, they would be completely invisible. This means our census of early galaxies is incomplete. We have only counted the brightest examples, missing entire populations too faint for direct detection. Lensing reveals this hidden majority. By targeting multiple lensing clusters and comparing results, astronomers estimate how many faint galaxies exist beyond detection limits. The numbers are staggering. For every galaxy we detect directly, perhaps 10 or 20 exist below the threshold, visible only through lensing. This changes cosmic census statistics. If the universe contains far more faint galaxies than we knew, total stellar mass is higher. Star formation rates need revision upward. Chemical enrichment happens faster. The universe was busier and more active at early times than direct observation suggested. Every lensed field adds to this story. JWST has observed dozens of lensing clusters, each revealing new distant galaxies. The catalog grows weekly. Each new detection refines our understanding of when galaxies formed, how many existed, what properties they had. But lensing has limits. Only certain configurations work. The lens must be massive enough. The background object must align properly. The distance geometry must be right. Most galaxies never get lensed by anything. We only see the lucky ones where alignment happened. This selection bias affects interpretations. Lensed galaxies might not represent typical galaxies. Maybe brighter galaxies appear more often in lensed surveys. Maybe certain types align better. Correcting for these biases requires careful statistical analysis. Despite complications, lensing remains invaluable. It pushes detection limits far beyond what any telescope could achieve alone. It maps dark matter distribution. It magnifies fine details for study. Einstein's prediction became astronomy's most powerful magnifying glass, and JWST wields that glass better than any previous instrument. The JADE survey targeted a region smaller than a grain of rice, held at arm's length. What came back from that tiny patch shocked the research team. 13 galaxies all formed within the first 500 million years after the Big Bang. 13 complete systems, each with stars, structure, chemical elements, all from the cosmic dawn period. Before JWST, astronomers knew of maybe 2 or 3 galaxies from this era. Hubble could detect hints, but lacked the infrared sensitivity to confirm distances. Ground telescopes saw even less. The cosmic dawn remained mostly invisible, hidden behind redshift that pushed light into wavelengths previous instruments could not capture effectively. Webb changed that instantly. Infrared sensors tuned precisely for high red shift detection turned cosmic dawn into an observable target. The first deep fields revealed what was always there, just invisible. Not one or two rare galaxies, but populations, clusters, collections of early structures. 13 in one small patch suggests thousands across the whole sky. Scale that up to the full celestial sphere, and the numbers become absurd. If this density holds everywhere, tens of thousands of cosmic dawn galaxies exist, each waiting for Webb to point in its direction and collect photons. This was not supposed to happen. Theoretical models predicted cosmic dawn galaxies would be rare, difficult to find. Each deep field might reveal one, maybe two examples. Surveys would need to cover enormous areas to build statistically significant samples. Instead, they cluster. The 13 galaxies in the Jade field are not randomly scattered. They group together, suggesting gravitational clustering already operated. Even at 500 million years after creation, matter had concentrated enough for galaxies to form preferentially in overdense regions. This confirms dark matter halos formed early. Without dark matter concentrations, galaxies would scatter randomly. The clustering pattern indicates dark matter had already clumped, creating gravitational wells where ordinary matter fell and ignited stars. The cosmic web's precursor existed by cosmic dawn. Studying 13 galaxies instead of one or two changes research possibilities dramatically. With one example, you cannot determine what is typical versus exceptional. With 13, statistical analysis becomes possible. You can measure average properties, identify outliers, track variations. The 13 showed surprising diversity. Some appeared compact, densely packed with stars. Others spread across larger regions, more diffuse. Some showed active star formation, bright in infrared. Others seemed quieter, older despite their young age. The variety suggested multiple pathways to galaxy formation operated simultaneously. This complexity challenges simple models. If all galaxies form through the same process, they should look similar at similar ages. The diversity indicates different environments, different dark matter halo masses, different gas conditions, all influenced outcomes. Chemical analysis added more surprises. Several of the 13 showed oxygen in their spectra. Oxygen requires stellar processing, stars living and dying, scattering elements into space. Finding it so early means stellar generations cycled quickly. First stars formed, lived brief lives, exploded. Second-generation stars incorporated those elements, created more, died. Third generation inherited richer chemistry, all within 500 million years. The timescale barely allows for this cycling. Massive stars live just a few million years. If only massive stars existed initially, generations could cycle faster. But building detectable oxygen levels requires many generations, hundreds or thousands of stellar lifetimes. Something accelerated the process beyond current models. One possibility, star formation happened in intense bursts. Instead of steady, gradual star production, early galaxies experienced episodes of extreme activity. Millions of stars ignited simultaneously, lived together, died together. Each burst enriched the gas dramatically, enabling faster chemical evolution. Another idea, the initial mass function was different. Modern galaxies produce mostly small stars with a few massive ones. Early galaxies might have reversed this, producing mostly massive stars. More massive stars mean faster cycling, quicker chemical enrichment, rapid evolution through stellar generations. Both remain speculative. What the 13 galaxies definitively proved, cosmic dawn was not a sparse, rare phenomenon. It was a busy, active period with abundant galaxy formation. The universe did not slowly wake from darkness. It exploded into light across vast regions simultaneously. The implications extend beyond just counting galaxies. If cosmic dawn was this active, reionization must have progressed faster than predicted. More galaxies mean more stars. More stars mean more ultraviolet radiation. More radiation means faster ionization of hydrogen throughout space. The fog cleared quickly. Within perhaps just 200 million years, stellar radiation ionized most hydrogen. The opaque early universe became transparent, allowing light to travel freely. This transformation enabled everything that followed. Every astronomical observation we make today, without reionization, the universe would remain dark, light, trapped, and scattered. The 13 galaxies of JDES contributed to that transformation. Their stars burned, their light spread, their radiation cleared space. Small individual contributions, but across thousands of similar galaxies, enough to change the cosmos. And we just started cataloging them. JWST captured something rare: galaxies in the act of merging. These are not modern merger events. These collisions happened billions of years ago, light from them only now reaching us. The images freeze ancient catastrophes mid-process, galactic collisions that took hundreds of millions of years to complete. Two systems approach each other, pulled together by mutual gravity. Initial contact is gentle. The galaxies are mostly empty space. Stars within them are so far apart that stellar collisions almost never happen. Galaxies pass through each other like clouds of gnats, interpenetrating without individual impact. But gravity does not pass through. Each galaxy's mass pulls on the other. Stars get deflected from their original orbits. Gas clouds collide directly. Unlike stars, when gas clouds hit, they compress, heat up, shock. Compressed gas collapses into new molecular clouds. Molecular clouds fragment and ignite stars. Merge events trigger star formation. Webb images show this happening in real time. Well, not real time. The mergers occurred billions of years ago, but we see the star formation, bright knots of newborn stars scattered through collision zones. Some merger systems produce stars hundreds of times faster than isolated galaxies. The collision disrupts organized structure. Spiral arms get torn apart, disks warp and twist. Material gets ejected into long tidal tails. Streams of stars and gas pulled away from both galaxies by gravitational forces. These tails extend millions of light years, thin threads of matter stretching into space. After initial pass-through, gravity pulls the systems back together. They swing around each other, interpenetrate again, separate again. Each passage sheds angular momentum through tidal forces and dynamical friction. The galaxies lose energy, spiral closer, eventually merge completely. The final product depends on the collision geometry. Head-on collisions destroy spiral structure, creating elliptical galaxies. Glancing merges might preserve some rotation, producing lenticular galaxies. Unequal mass merges, where one galaxy is much smaller, sometimes leave the larger galaxy relatively intact, while the smaller one gets shredded. JWST found merger systems at all stages. Some show galaxies just beginning to interact, barely touching. Others show full interpenetration, gas clouds colliding violently. Still others show late-stage merges, two nuclei spiraling together in the final approach before coalescence. Each stage reveals different physics. Early interactions show tidal forces at work, pulling material into streams. Mid-stage merges showed gas and triggered star formation. Late stages show nuclei approaching, separated by just thousands of light years, about to merge into a single massive core. When nuclei merge, supermassive black holes at galaxy centers approach each other. Each galaxy harbors a central black hole. As galaxies merge, those black holes spiral toward each other, eventually forming a binary system. The binary decays through gravitational wave emission, ultimately merging in a burst of radiation that JWST cannot detect directly. But the aftermath is visible. Merged black holes accrete gas violently, lighting up as quasars. JWST detected several merger systems, showing quasar activity. Evidence that black hole merges recently occurred or are occurring. The quasar phase eventually fades as gas depletes. leaving a quiet elliptical galaxy with one massive central black hole. Merger frequency affects galaxy evolution dramatically. In dense environments like galaxy clusters, merges happen constantly. Galaxies collide, merge, grow through accretion of neighbors. In sparse environments, galaxies evolve in isolation, rarely encountering anything to merge with. The early universe was dense everywhere. Galaxies formed closer together. Space had not expanded as much. Merger rates were higher, perhaps 10 or 20 times higher than today. Most early galaxies experience multiple merges in their first few billion years. This rapid merging explains massive elliptical formation. You cannot build a giant elliptical in isolation. You need multiple mergers combining several smaller galaxies into one large system. High merger rates in the early universe allowed this to happen quickly. JWST's images confirmed merger activity peaked around 10 billion years ago. At that epoch, roughly 30% of galaxies showed clear merger signatures. Today, the rate drops to maybe 5%. The universe has calmed. Space expanded enough that galaxies sit farther apart, reducing encounter frequency. But merges still happen. Andromeda and the Milky Way will collide in about 4 billion years. The merger will take billions of years to complete, reshaping both galaxies into a single elliptical system. Observers on planets in that future galaxy will see a very different night sky. Watching ancient mergers through JWST gives us preview of our own future. The processes we observe in distant galaxy collisions will happen locally. Gas clouds will compress and ignite, star formation will spike, tidal forces will create streams. Eventually, two nuclei will spiral together, two black holes will merge. The collision is inevitable, already in motion. Andromeda approaches at about 70 miles. Nothing can stop it. Gravity guarantees the collision. We watch distant examples to understand what awaits us. Yet despite violence on galactic scales, individual stars remain safe. The vast emptiness of space protects them even during direct collision. Stars pass through gaps between other stars. Planets survive. Life could persist through merger events, watching the sky transform, but experiencing no direct catastrophe. The real danger comes from the central black hole merger. Gravitational waves and jets from the merged black hole could sterilize regions near the galactic core, but most stars orbit far from the center, safe from direct effects. The merger reshapes the galaxy without destroying most stellar systems. And billions of years later, a new stable configuration emerges. Two numbers refuse to agree. The expansion rate of the universe can be measured two ways. Each method is precise, well-tested, verified by independent teams. Both should give the same answer. They do not. Measure expansion by looking at the cosmic microwave background. This ancient light from 380,000 years after the Big Bang encodes information about cosmic properties. Tiny temperature variations map density fluctuations that later grew into galaxies. By analyzing these variations, cosmologists calculate how fast space expands. The answer about 67 km/s per megapar. This means for every megapark of distance, roughly 3.3 million light-year. Space expands at 67 km/s. Double the distance, double the expansion speed. It is a clean, consistent relationship. Now measure expansion differently. Look at nearby galaxies with known distances. Measure their red shift to see how fast they recede. Divide recession speed by distance. This gives expansion rate directly from local observations. The answer about 73 km/s per megasec, 6 km/s difference. That sounds small. It is not. The measurements are precise to within 1%. A 6-unit difference is highly significant statistically. One or both measurements must be wrong or something is missing from our understanding. Astronomers call this the Hubble tension. JWST was supposed to help resolve it. The telescope can measure distances to faraway galaxies more precisely than previous instruments. Better distances mean better expansion calculations. Everyone expected JWST to clarify which measurement was correct. Instead, JWST made the tension worse. New distance measurements confirmed the higher expansion rate of 73 km per megapar. This strengthened the local measurement, making the discrepancy with cosmic microwave background measurements even harder to explain. Something is genuinely wrong. Either our understanding of the early universe is incomplete, or our local distance measurements have systematic errors, or the expansion rate actually varies across cosmic time in unexpected ways. One possibility: dark energy behaves differently than assumed. Standard cosmology treats dark energy as constant, pushing space apart at a steady rate. If dark energy's strength varied over billions of years, early universe measurements and late universe measurements could give different answers without either being wrong. This requires modifying general relativity. Einstein's equations allow for changing dark energy, but most versions create other problems. They predict cosmic structures that do not exist or expansion histories that conflict with other observations. Making dark energy vary just right to fix Hubble tension without breaking everything else is extremely difficult. Another idea: the early universe contained extra radiation. More radiation in the early cosmos would change cosmic microwave background calculations, shifting the predicted expansion rate. If some unknown particle or field contributed radiation energy, it could reconcile the measurements. But this requires inventing new physics. No particle in the standard model provides the needed radiation. Any solution requires something beyond current theory. Scientists prefer fixing problems with known physics before adding new particles. A third option: distance measurements have hidden errors. The local expansion measurement depends on a ladder of distances. First, measure distances to nearby stars using parallax. Second, calibrate standard candles like Cepheid variables. Third, use Cepheids to calibrate supernovae. Fourth, use supernovae to measure distances to distant galaxies. Each step introduces potential error. If Cepheid calibration is wrong, everything built on it collapses. If supernovae are not as standard as believed, distances calculated from them are unreliable. Small errors in early ladder rungs get magnified at later rungs. JWST tested the ladder carefully. The telescope observed Cepheids in distant galaxies, measuring their properties more precisely than Hubble could. The results confirmed. Cepheid calibrations are solid. This eliminates one possible error source, but deepens the mystery. The tension now sits at statistical significance exceeding 5 sigma. In particle physics, 5 sigma means discovery. The effect is real, not a statistical fluke. Applying the same standard to Hubble tension suggests the discrepancy is genuine, requiring explanation beyond measurement error. What terrifies cosmologists is the implication. If the tension is real, our standard cosmological model is wrong. Not slightly inaccurate, fundamentally wrong. The model that explains cosmic microwave background observations, galaxy distributions, large-scale structure, everything fails to explain expansion rate measurements. This would require rewriting cosmology, not tweaking parameters, not adjusting assumptions, potentially replacing the entire framework with something new. Decades of careful model building would need revision. Alternative explanations exist, but seem unlikely. Maybe we live in a cosmic void, a region with lower than average density. Expansion might behave differently in voids. This could create local measurements that do not match global average, but we see no evidence for such a void. Surveys map matter distribution around us. The data show we live in a fairly typical region, not a significant underdensity. The void explanation requires a void we have not detected, or maybe gravity behaves differently than general relativity predicts. Modified gravity theories exist. Most fail to match observations. A few survive scrutiny but require fine-tuning that feels contrived. They solve Hubble tension by creating other problems. The cleanest solution would be finding a hidden, systematic error. some subtle mistake in how we measure distances or interpret red shifts. An error that multiple independent teams all made the same way, possible but increasingly unlikely as checks multiply. JWST continues collecting data. Each new measurement either narrows the tension or confirms it. So far, confirmation dominates. The expansion rate discrepancy holds across different methods, different distance indicators, different samples. The universe is telling us something important. Empty space pushes everything apart. This sounds impossible. Emptiness cannot push. But quantum field theory predicts that vacuum itself contains energy. That energy has pressure, negative pressure. Instead of pulling things together like normal pressure, negative pressure pushes them apart. This is dark energy. We cannot see it directly. We infer its existence from cosmic acceleration. The universe does not just expand. The expansion speeds up. Galaxies recede faster now than they did billions of years ago. Something is pushing against gravity, overwhelming attraction with repulsion. Measurements show dark energy constitutes 70% of the universe's total energy density. Matter, both ordinary and dark, comprises the other 30%. This means most of the universe consists of something we do not understand, something that behaves oppositely to everything else. The acceleration was discovered in the late 1990s. Two teams independently measured distances to distant supernovae. They expected to find deceleration from gravity slowing expansion. Instead, distant supernovae appeared farther away than predicted. The universe was accelerating. The discovery won a Nobel Prize. It also shattered comfortable assumptions. Before, cosmologists worried about whether expansion would slow enough to reverse, causing eventual collapse. Acceleration eliminated that possibility. Expansion will continue forever, accelerating perpetually. JWST refined measurements of acceleration strength. By observing distant galaxies at multiple red shifts, astronomers map how expansion rate changed over time. The data revealed dark energy's influence grew as the universe aged. Early on, matter dominated. Gravity slowed expansion. Then dark energy took over, reversing deceleration into acceleration. The transition happened about 6 billion years ago. Before then, expansion was slowing, after it was speeding up. We live in an accelerating epoch, watching distant galaxies race away faster every moment. Dark energy's properties remain mysterious. Is it truly constant vacuum energy, unchanging forever? Or does it evolve, growing stronger or weaker with time? The simplest assumption, constant dark energy, fits most observations, but small deviations might exist, detectable only with extremely precise measurements. JWST helps test this. By measuring acceleration at different cosmic times, the telescope constrains how dark energy strength varied. So far, constant dark energy fits the data well, but uncertainties remain large enough to hide small variations. The theoretical problem with dark energy is its magnitude. Quantum field theory predicts vacuum energy should exist, but calculations produce values 120 orders of magnitude larger than observed. This is cosmology's worst prediction ever. Something must suppress vacuum energy to nearly zero, but not quite zero. Nobody knows what. Many theories attempt to explain this. Most involve new physics beyond the standard model. Some propose extra dimensions. Others suggest our universe is one bubble in a multiverse where different bubbles have different vacuum energies. We happen to exist where vacuum energy is small enough to allow galaxies and stars. This anthropic argument feels unsatisfying. It explains the value by saying we could not exist if it were different. True, but not predictive. It offers no mechanism, no testable consequence, no path toward deeper understanding. Alternative explanations modify gravity itself. Maybe Einstein's equations need correction at cosmic scales. Modified gravity could mimic dark energy's effects without requiring vacuum energy. But most modified gravity theories fail other tests, predicting galaxy rotation curves that do not match observations or cosmic microwave background patterns that differ from measurements. The simplest explanation remains a cosmological constant. Einstein originally added this to his equations, then called it his greatest blunder when expansion was discovered. Now it seems he was right the first time. A constant term in the equations represents dark energy naturally, but calling it simple does not make it understood. What is vacuum energy physically? Why does it have the value it does? How does it push space apart? These questions lack satisfying answers. We describe dark energy mathematically but do not truly comprehend it. The acceleration it causes creates a future very different from the past. As expansion accelerates, distant galaxy clusters recede faster and faster. Eventually, they cross the cosmic horizon, moving away faster than light can traverse expanding space between us. At that point, light from those clusters can never reach us again. The visible universe will shrink, not in physical size. Space will continue expanding, but the number of galaxies we can observe will decrease. One by one, distant structures will fade beyond detection, their light too redshifted and dispersed to register. In trillions of years, only our local galaxy cluster remains visible. Everything else will have receded beyond the cosmic horizon. Future observers will see a nearly empty universe, just a small collection of nearby galaxies in an otherwise dark sky. They will have no way to know billions of other galaxies existed, lost beyond reach. This isolation is dark energy's final consequence. It does not just accelerate expansion. It eventually tears the universe apart at the largest scales, breaking connections between galaxy clusters, isolating each cluster in its own island of space, and there is no way to stop it. The abyss void terrifies by its absence. 330 million light-year across, this region contains almost nothing. A few dozen galaxies scatter through a volume that should hold tens of thousands. It is a hole in the universe, a bubble in the cosmic foam where matter fled toward denser regions. Astronomers discovered it in the 1980s. Galaxy surveys mapping three-dimensional positions found an enormous gap. At first, researchers thought it was a data error, equipment failure, or selection bias, creating an artificial empty region. Repeated observations confirmed it was real. Matter had evacuated. Voids form naturally in cosmic structure. The Big Bang created tiny density variations. Regions slightly denser than average attracted more matter through gravity. Regions slightly less dense lost matter to denser neighbors. This created a positive feedback loop. Dense regions got denser. Sparse regions got emptier. Over billions of years, matter drained from under dense areas flowing toward over-dense regions. The cosmic web emerged from this process. Filaments formed where matter concentrated. Voids expanded where matter left. But the beta's void is extreme. Most voids measure tens of millions of light-years across. The bua's void stretches over 300 million. The size challenges formation models. Creating a void this large requires either extremely low initial density or billions of years for matter to evacuate. The universe's age barely allows time for voids this size. JWST observations do not target voids directly. Empty regions offer little to observe, but mapping the cosmic web around voids reveals their boundaries, their shapes, their relationship to surrounding structure. Voids are not perfectly empty. A few galaxies exist inside, perhaps 60 confirmed in Boets. These galaxies are strange. Most appear small, dim, isolated. Star formation rates are low, gas reserves are depleted. They look old, exhausted, abandoned. Living in a void seems to stunt galaxy development. Without neighbors, galaxies cannot merge. Without nearby gas clouds, they cannot replenish star-forming material. They burn through their resources, then fade. The void becomes a galaxy graveyard where evolution stalls. But void boundaries are different. Where void meets filament, galaxies cluster densely. Matter evacuating the void accumulates at edges, creating walls of galaxies. Some of these walls span hundreds of millions of light-years. Thin sheets of matter enclosing empty volumes. The largest structures in the universe are void surfaces. The Great Wall of Galaxies stretches 1.3 billion light-year, a sheet of matter between two supervoids. Other walls exist, separating other voids. The cosmic web resembles Swiss cheese with holes surrounded by dense surfaces. This foam-like structure emerged naturally from gravity. No special physics required. Simple attraction and expansion create the pattern. Dense regions pull matter in. Expansion drives voids apart. The interplay produces foam. What puzzles cosmologists is the scale. Simulations recreate void formation successfully at small scales. Reproduce the Beteta's void size requires very specific initial conditions. The density fluctuations needed are rare statistical outliers. Finding even one supervoid might be lucky. JWST's wide field surveys aim to map void distribution across cosmic time. Do voids grow as the universe ages? Do they maintain constant size? The answers constrain cosmological models. Early results suggest voids were smaller in the past. At high redshift, voids measured perhaps 100 million light-year across. By today, they stretch to 300 million or more. Cosmic expansion drives this growth, pushing void boundaries apart as space expands. But dark energy affects void evolution. Accelerating expansion should make voids grow faster. In recent times, gravity's pull weakens as matter spreads apart. Dark energy's push strengthens as space expands. The balance tips toward expansion, accelerating void growth. This creates a future where voids dominate. In hundreds of billions of years, matter will concentrate into ever denser nodes, separated by ever larger voids. The universe becomes mostly empty space with rare islands of matter. Galaxy clusters shrink into isolated specks in a vast, dark ocean. Eventually, even those specks separate. Accelerating expansion tears apart galaxy clusters, then galaxies themselves, then solar systems. In the extreme far future, every bound structure dissolves as expansion overcomes all gravity. But that lies trillions of years away. For now, voids are just empty regions, strange but stable. They offer laboratories for studying low-density environments. What happens to galaxies without neighbors? How does isolation affect evolution? The few void galaxies observed are dwarfs mostly, small systems with low mass, dim light, little ongoing activity. They might be remnants of larger galaxies that lost mass through interactions before entering the void. Or they might be primordial dwarfs that never grew larger. Without mergers, growth is difficult. Galaxies in dense environments grow by accreting neighbors. Void galaxies have no neighbors to accrete. They can only grow by pulling in sparse gas from surrounding space. That process is slow, insufficient for building large systems. The result is stunted population. Void galaxies represent a path not taken elsewhere. Isolated evolution without mergers, without strong environmental effects. Studying them reveals what galaxies become when left alone. The answer seems to be small, quiet, fading. Voids also affect cosmological measurements. When light crosses a void, it experiences less gravitational potential. This shifts photon energy slightly, creating a detectable signature. By measuring this effect across multiple voids, astronomers test general relativity at cosmic scales. So far, relativity passes every test, but precision improves with better void maps. JWST's contribution comes from identifying high red shift voids, extending the test to earlier cosmic times. If relativity breaks down at large scales, the effect might show up differently at different epochs. Finding that breakdown would revolutionize physics. For now, voids remain empty, strange, and tantalizingly mysterious. There is a horizon we can never cross, not because of technology limits, not because of distance, because space itself expands faster than light can traverse it beyond a certain point. That point marks the edge of the observable universe, currently sitting 46 billion light-years away. Wait, 46 billion years, but the universe is only 13.8 billion years old. This confuses people constantly. How can we see farther than light has had time to travel? The answer is expansion. Light from the cosmic horizon began traveling toward us when the universe was young. Back then, that horizon was much closer, perhaps just millions of light years away. But during its journey, space expanded. The light traveled its full journey, always moving at light speed, but the expansion added distance. Think of running on an expanding track. You run normally, never speeding up, but the finish line moves away as the track stretches. By the time you arrive, the track is much longer than when you started. Photons from the cosmic horizon experience this. They departed 13.8 billion years ago. At the moment the universe became transparent. During their journey, space expanded. The starting point receded. By the time photons reach us, their birthplace sits 46 billion light years distant. This is the observable universe's radius. Double it for diameter, 93 billion light-year from edge to edge. Everything in that sphere can, in principle, be observed. Everything beyond cannot. The horizon is not a physical barrier. No wall exists at 46 billion light-year. Space continues beyond it. Galaxies exist there, but light from beyond the horizon will never reach us ever. Waiting trillions of years would not help. Here is why. Expansion accelerates. Dark energy pushes space apart faster with each passing moment. Regions beyond the current horizon recede faster than light can approach us through expanding space. Light from those regions makes progress toward us, but expansion carries the source away faster than progress occurs. It is like running on a treadmill that accelerates. You run forward at maximum speed, but the treadmill speeds up faster than you run. You never reach the end. You might even lose ground, moving backward relative to the endpoint despite running forward at top speed. Light from beyond the horizon faces this fate. It travels toward us continuously, never stopping, never slowing, but expansion wins. The photons lose ground, falling farther behind rather than getting closer. This creates a permanent limit on observation. We can build telescopes 1,000,000 times more powerful than JWST. We can observe for billions of years. We will never see beyond the cosmic horizon. The universe conceals everything past that line. What makes this hard limit particularly frustrating? We know things exist there. The universe does not stop at 46 billion light-year. If space is flat and infinite, galaxies continue forever. Trillions upon trillions of galaxies, each with billions of stars extending without end in all directions. We can never observe any of it. The portion of reality accessible to observation might represent a tiny fraction of what exists. Imagine living in a room with one window. The window shows a view of the outside world, but most of the world lies beyond what the window can show, except worse than that, because the window could show more if you moved it. The cosmic horizon cannot be moved. It is not a limit on our instruments. It is a limit on possible observation from any instrument anywhere ever. Future civilizations will face the same limit. Actually, a shrinking limit. As expansion accelerates, the cosmic horizon contracts, not in absolute distance, but in what we can observe. Galaxies currently visible will eventually cross the horizon, receding beyond detection. In trillions of years, only our local galaxy cluster remains visible. Everything else will have faded beyond the horizon. Future observers will see almost nothing. They will have no evidence that other galaxies ever existed, no way to reconstruct cosmic history, no data to test cosmological theories. They will be isolated in a nearly empty universe. This is the ultimate fate of observation. Accelerating expansion erases evidence of the broader cosmos. Knowledge becomes impossible. Future scientists might conclude the universe consists of one galaxy cluster in otherwise empty space. They would be wrong, but have no way to know it. We live in a special time right now. Today the universe is old enough for structures to have formed, but young enough for most of them to remain visible. Webb can observe cosmic history from near the Big Bang to the present. Miss this window and observation becomes impossible. A civilization arising trillions of years from now would never discover the Big Bang, never measure cosmic expansion, never detect distant galaxies. Their physics would be fundamentally incomplete, missing crucial evidence. This temporal privilege carries responsibility. We must observe and record while observation remains possible. Document the cosmic web before expansion tears it apart. Map the universe before most of it recedes beyond reach. JWST contributes to this effort. Every deep field captures galaxies that future civilizations cannot see. Every spectrum records data that will eventually be lost. The telescope preserves knowledge before expansion erases it. In a sense, we are archivists for the future, collecting information, storing it, passing it forward to civilizations that will arise after observation windows close. They will inherit our data, but never verify it. They must trust our records, because they cannot repeat our observations. The cosmic horizon is absolute. No technology can overcome it. No physics can extend it. Light from beyond the horizon will never arrive. That portion of the universe remains forever unknown. And with accelerating expansion, the unknown portion grows larger every day. Einstein said, "Nothing can move faster than light." He was right. Nothing can move through space faster than light, but space itself has no speed limit. Space can expand as fast as it wants. And when space expands fast enough, objects riding that expansion can recede from each other faster than light could travel between them. This is happening right now. Distant galaxies recede from us faster than light speed, not because they move through space quickly, because space expands between us, carrying them away. The distinction is crucial. Imagine dots on a balloon. Inflate the balloon. Dots separate as rubber stretches. The dots do not move across the rubber. The rubber itself expands, carrying dots apart. Now inflate the balloon faster. Dots on opposite sides separate faster than a bug could crawl across the surface. Space expands like the balloon. Galaxies are dots. Space is rubber. Expansion carries galaxies apart faster than light could travel the expanding distance between them. This does not violate relativity. Relativity limits motion through space. It says nothing about space's own expansion rate. Beyond a certain distance, every galaxy recedes faster than light. That distance is roughly 14 billion light-year. Currently, any galaxy farther than this recedes superluminally. Not all of them started that way. Some began closer, receding slower than light. Then expansion accelerated. Now they exceed light speed. Once a galaxy crosses into superluminal recession, light from it can still reach us. This surprises people. How can light from a superluminal object ever arrive? The key is expansion's gradient. Close to us, expansion is slow. Far away, expansion is fast. Light emitted from a distant galaxy travels through expanding space, gradually entering regions where expansion is slower. Think of swimming upstream in a river. The current far upstream might be faster than you can swim, but as you swim downstream, the current gradually slows. Eventually, you reach a section where current is slower than your swimming speed. You make progress downstream from there. Light does the same in expanding space. Emitted from a galaxy receding faster than light, the photon initially loses ground. Expansion carries it backward relative to us. But as it travels, it enters regions where expansion is slower. Eventually, expansion becomes slower than light speed, and the photon makes forward progress. Given enough time, the photon reaches us. This allows Webb to see galaxies receding faster than light. Most of the galaxies in deep field images recede superluminally. Right now, light from them left billions of years ago when they were closer and receding slower. That light crawled through expanding space, fought against expansion, gradually won, and finally arrived. But here is the critical point. While old light from superluminal galaxies can reach us, new light cannot. Any photon emitted today from a galaxy currently receding faster than light will never reach us. Expansion will carry it backward forever. It might travel billions of light years toward us, but expansion carries its source away faster. The photon never catches up. This creates a strange situation. We see galaxies as they were billions of years ago. Light from that era reaches us, but light from their present state never will. We watch frozen history, unable to observe current events. Some galaxies visible in Webb images have already crossed a different threshold, not just superluminal recession. Beyond the cosmic event horizon, this is the point where, even accounting for slowing expansion in local space, photons can never make forward progress. Galaxies beyond this horizon are lost forever. Light they emitted in the past might still arrive, but no new information will ever reach us from them. They could explode, merge, vanish entirely. We would never know. The last photons from those galaxies are already in transit. Once those arrive, the galaxy disappears from our observable universe permanently. The cosmic event horizon sits closer than the observable universe boundary. Currently, it rests around 16 billion light-years away. Galaxies beyond this point are visible if they existed in the past and light already began its journey. But they are beyond future observation. We see their ghosts, not their present state. As expansion accelerates, this horizon shrinks. More galaxies cross it every day. Within trillions of years, almost everything will have crossed beyond reach. The observable universe will contract dramatically, leaving only our local galaxy cluster visible. This creates what cosmologists call the horizon problem in reverse. Originally, the horizon problem asked how distant regions appear so similar despite no time for light to cross between them. Inflation solved that. The reverse problem asks how future observers will have no access to evidence supporting inflation, cosmic expansion, or the Big Bang. They will be trapped in informational poverty. Unable to see beyond their local cluster, future scientists will lack data needed to reconstruct cosmic history. They might develop incorrect theories, unable to test them against distant observations. Our current epoch represents a narrow window when both structure and observability exist. This motivates documenting as much as possible. Now, every galaxy Webb observes might eventually cross the horizon. Every spectrum captured might be the last information we receive from that system. The urgency is not technological, it is cosmological. We race against expansion, not to travel anywhere, to observe before observation becomes impossible to measure, while measurement remains feasible. JWST contributes to this effort, pushing observation to the edge of what will ever be observable. The superluminal recession of distant galaxies is not science fiction. It is measured fact. We calculate recession velocities from redshift. The numbers exceed light speed for most of JWST's targets. This does not break physics. It reveals space's ability to expand without limit, and it proves that what we see is not all that exists. Beyond the observable universe, countless galaxies recede faster than light, forever beyond detection. They are as real as anything. Webb images, but separated from us by expansion, too rapid to overcome. We will never see them. They will never see us. Expansion has already created permanent separations across the cosmos. Oxygen should not exist yet. Webb spectrographs split light from an early galaxy into component wavelengths. The data revealed emission lines matching oxygen atoms. These atoms formed less than 500 million years after the Big Bang, an era when the universe supposedly contained only hydrogen and helium. Oxygen is a death signature, stars created in their cause through nuclear fusion. Helium fuses into carbon, carbon fuses into oxygen. When massive stars explode as supernovae, they scatter these elements across space. Next-generation stars incorporate them, create more, die, and scatter them again. This process requires time. A massive star lives perhaps 3 million years before exploding. Its debris spreads, cools, collapses into new molecular clouds. New stars ignite from enriched material. They live their own lifetimes, some millions of years, others billions. Each generation adds more heavy elements to the cosmic mix. Finding oxygen in cosmic dawn galaxies means multiple stellar generations already cycled. First stars formed from pure hydrogen and helium. They burned, died, scattered elements. Second generation stars formed from slightly enriched gas. They created more oxygen, more carbon, more nitrogen. Third generation stars inherited richer chemistry. Still all within 500 million years after creation, the timeline compresses impossibly, even with rapid stellar evolution. Fitting 3 or more generations into 500 million years challenges models. Something must have accelerated the cycling beyond current predictions. One theory proposes the first stars were hypergiants. Population 3 stars formed from pristine gas might have reached masses hundreds or thousands of times larger than modern stars. At such extreme masses, nuclear fusion runs at furious rates. A star that massive might live only 10,000 years before exploding. 10,000 years instead of 3 million. Rapid cycling would allow hundreds of stellar generations within a few 100 million years. Each generation contributes oxygen. Concentrations build quickly. By 500 million years, detectable amounts exist. But hypergiant stars remain theoretical. No confirmed population 3-star has ever been observed. We infer their properties from models and from chemical signatures in ancient gas clouds. Making them massive enough to explain JWST's oxygen detection requires pushing models to extreme limits. Another possibility involves star formation efficiency. Modern galaxies convert maybe 1% of available gas into stars per million years. Early galaxies might have operated at 10 or 20% efficiency. More stars forming simultaneously means more dying simultaneously. More elements scattered simultaneously. Higher efficiency accelerates enrichment, but this creates its own problems. Too much star formation depletes gas quickly. Galaxies should exhaust fuel and go quiet. Yet many early galaxies Webb observes show ongoing star formation, suggesting they retained gas despite earlier bursts. The oxygen detection also reveals galaxy properties. Emission lines come from excited atoms in star-forming regions. Hot young stars ionize surrounding gas, creating glowing nebula. Oxygen in those nebula traces recent star formation. The brightness of oxygen lines indicates how vigorously stars are forming. Some cosmic dawn galaxies form stars at rates hundreds of times faster than modern galaxies. This extreme activity cannot sustain indefinitely. Eventually, gas depletes or gets heated so much it cannot collapse. The burst phase ends. The galaxy fades into quiescence. We might be catching these systems during brief explosive episodes. Chemical composition also affects later evolution. Oxygen and carbon enable molecule formation. Molecules cool gas more efficiently than atoms alone. Cooler gas collapses more easily. More collapse means more star formation. Heavy elements from early stellar generations facilitate subsequent generations. This positive feedback could explain rapid galaxy development. Once a galaxy creates some heavy elements, those elements make further star formation easier. The process snowballs. What starts slowly accelerates exponentially. Early galaxies might have crossed a threshold where enrichment triggered runaway star formation. JWST's detection changes our understanding of cosmic chemical evolution. Previously, astronomers thought metal enrichment happened gradually over billions of years. The universe started pure, slowly accumulated heavy elements, eventually reached modern chemical abundance. Now we know enrichment began almost immediately. The cosmic dark ages were brief. Within a few 100 million years, stars formed, died, enriched their surroundings. By 500 million years, some galaxies already showed chemical signatures similar to much older systems. The universe evolved chemically faster than cosmological models predicted. This has implications for planet formation. planets require heavy elements. You cannot build rocky worlds from pure hydrogen and helium. Earth contains iron, silicon, oxygen, carbon, all created in stars. If heavy elements appeared early in cosmic history, planet formation could have begun early as well. Perhaps rocky planets existed when the universe was less than 1 billion years old. If planets formed early, life might have emerged early. Billions of years before Earth formed, other worlds might have hosted chemistry complex enough for biology. We might not be the first technological civilization, just the current one. The oxygen in cosmic dawn galaxies opens this possibility. Every oxygen atom detected represents stellar processing, nuclear fusion, supernova explosions. The machinery for creating complex chemistry operated from the beginning. The universe wasted no time building the periodic table, and if chemistry came early, everything else could follow. The brightest objects in the early universe are also the most mysterious. Quasars shine across billions of light years, outshining entire galaxies. JWST confirmed dozens existed less than 1 billion years after the Big Bang. Each one harbors a supermassive black hole at its core, mass equivalent to 1 billion stellar masses, feeding violently on surrounding gas. That mass should not exist yet. Building a billion-mass black hole requires accumulating matter for hundreds of millions of years. Gas must fall in, cross the event horizon, add to the central mass. The process has limits. Accretion generates radiation. Radiation pushes gas away. Too much radiation stops accretion entirely. This creates a maximum growth rate called the Eddington limit. A black hole can only double its mass every few tens of millions of years without exceeding this limit. Start with a 100-mass black hole from the first stellar collapse. Let it accrete at maximum rate. By 1 billion years after the Big Bang, it reaches maybe 100,000 stellar masses. Not 1 billion yet. JWST found quasars with billion-mass black holes at exactly this epoch. The growth timeline does not work. Either black holes grew faster than the Eddington limit allows, or they started much more massive than stellar collapse produces. Both options require new physics. Super Eddington accretion might occur in special conditions. If gas falls in from all directions simultaneously, radiation cannot escape efficiently. Trapped radiation cannot push gas away effectively. The black hole grows faster, possibly 10 or 100 times faster than normal. This explains rapid growth but requires specific geometry. Gas must flow spherically, symmetrically, maintaining perfect balance. Any asymmetry breaks the setup. Jets form, radiation escapes, accretion slows. Sustaining super Eddington conditions for hundreds of millions of years seems unlikely. The alternative is more radical. What if the first black holes formed massive from the start? Instead of stellar collapse producing 100-mass black holes, maybe direct collapse of enormous gas clouds produced 10,000 or 100,000 mass seeds. This shortens the required growth time dramatically. Start with 100,000 mass seed, accrete at Eddington limit for 700 million years, reach 1 billion masses by the time quasars appear. The timeline works perfectly, but direct collapse requires special conditions. Normal gas clouds fragment when they collapse. Fragmentation creates many small objects instead of one large one. Preventing fragmentation requires keeping gas hot, suppressing molecule formation that would enable cooling and fragmentation. How do you keep primordial gas clouds hot? One idea involves intense ultraviolet radiation from nearby stars. If first-generation stars ignite near a gas cloud, their radiation photo dissociates molecules, preventing cooling. The cloud remains hot, cannot fragment, collapses directly into a massive black hole. This works in simulations but requires precise timing. Stars must ignite close enough to irradiate the cloud, but not so close that they disrupt it. The window is narrow. Finding enough such configurations to explain all observed quasars seems difficult. JWST cannot see the black holes directly. Black holes emit no light. We detect them through their effects. Gas falling toward a black hole heats to millions of degrees, glowing brilliantly. The glowing accretion disk outshines the entire host galaxy. That is what makes quasars so bright. But the disk obscures details. We cannot see the black hole's event horizon or measure its properties directly. We infer mass from disk luminosity and from motion of nearby gas. The gas orbits the black hole at speeds determined by gravitational pull. Faster orbits mean more massive black hole. Spectroscopy reveals these orbital speeds. Emission lines from gas get Doppler shifted by motion. Gas approaching us shows blue shifted lines. Gas receding shows red shifted lines. The width of emission lines reveals velocity range. Wider lines mean faster orbits, mean more massive black hole. Early quasars show extremely wide lines. Some indicate orbital velocities reaching thousands of miles s. Only billion-mass black holes generate such speeds. The measurements are solid, verified by multiple independent teams. The mystery deepens when considering black hole and galaxy coevolution. Modern supermassive black holes correlate with their host galaxy properties. More massive galaxy, more massive black hole. The relationship is tight, suggesting they grew together, influenced each other's development. Early quasars show this relationship already established. Less than 1 billion years after creation, black holes and galaxies had already synchronized their growth. This means whatever process couples them operated immediately from the earliest epochs. Quasar feedback might explain this. When a black hole accretes gas violently, it generates powerful jets and winds. These outflows slam into surrounding galaxy gas, heating it, pushing it away. Heated gas cannot collapse to form stars. The black hole regulates its own fuel supply and the galaxy's star formation simultaneously. This self-regulation creates the observed correlation. Black hole grows, outflows intensify, star formation suppresses. Galaxy growth slows until black hole quiets. Balance emerges naturally from feedback cycles, but establishing this balance in just a few 100 million years requires rapid feedback responses. Early quasars were more active than modern ones. JWST detects quasars at high redshift at rates higher than expected. The early universe had more active supermassive black holes than later epochs. Perhaps accretion was easier when galaxies were gas-rich and compact. Or perhaps we see a phase that every galaxy experiences briefly. All galaxies might have gone through a quasar phase early in their history. Most have since quieted as gas depleted. We catch early galaxies during their active phase because that is when they were. Modern galaxies have supermassive black holes too, just dormant. The Milky Way's central black hole masses 4 million times our stellar home. It barely accretes anything currently. If you dropped gas into it, it could become a quasar again. The potential remains just inactive. Early quasars show us what our galaxy might have looked like billions of years ago. Violently active, brilliantly luminous, feeding voraciously. The transition from quasar to quiet galaxy represents a major phase in cosmic evolution. JWST documents this transition by observing galaxies at many different ages, and the billion-mass black holes powering early quasars remain as mysterious as ever. Before galaxies, before planets, before any structure existed, the first stars ignited. Population 3 stars formed from pure hydrogen and helium, pristine gas untouched by stellar processing. No heavy elements existed yet to contaminate their composition. These stars were fundamentally different from anything burning today. They were massive beyond modern comparison. Current models suggest population 3 stars reached masses from 100 to 1,000 times larger than our own stellar home. At such extreme masses, core temperatures soared. Nuclear fusion ran at furious intensity. Surface temperatures reached 50,000 star, 3 times hotter than modern massive stars. That heat changed everything about how they functioned. Hot stars emit most energy as ultraviolet radiation. Population 3 stars blazed with UV intensity that modern stars cannot match. This radiation flooded surrounding space, ionizing hydrogen atoms, creating bubbles of ionized gas, expanding outward at thousands of miles ss. These ionization bubbles transformed the early universe. Before first stars, space was dark and neutral. Hydrogen atoms remained intact, electrons bound to protons. Neutral hydrogen absorbs light, making the universe opaque, but ionized hydrogen lets light pass freely. Each population 3 star cleared a transparent bubble around itself. As more stars ignited, bubbles merged. Gradually, ionization spread through the cosmos. Within perhaps 200 million years, most hydrogen was ionized. The universe became transparent. Light could travel freely. This epoch, called reionization, fundamentally altered cosmic conditions. Population 3 stars lived fast and died violently. A 1,000 mass star burns through its fuel in just a few million years. Some models suggest as little as 2 million years from ignition to explosion. Compare this to our own stellar home, which will last 10 billion years total. Population 3 stars compressed entire lifetimes into eye-links. When they died, they exploded as hypernovae. Regular supernovae release about 1 pho of energy, roughly 10 to the 51 ERGs. Population 3 hypernovae might have released 100 times more. The explosions were so powerful, they completely disrupted the star, leaving no remnant, no neutron star, no black hole, total annihilation. But first, they scattered elements. During their brief lives, population 3 stars fused hydrogen into helium, helium into carbon, carbon into oxygen. The most massive cores created elements all the way to iron. Hypernova explosions scattered these elements across thousands of light years. This seeded the universe with the first heavy elements. Subsequent stars formed from slightly enriched gas. These population 2 stars incorporated trace metals from population 3 deaths. Their chemistry was different, their evolution different, their properties different. Nobody has ever directly observed a population 3 star. They all died billions of years ago. Their lifetimes were too short for any to survive until today. We know they existed only from indirect evidence. Chemical signatures in ancient gas clouds show patterns consistent with population 3I enrichment. Some extremely metal-poor stars in the Milky Way might be population 2 stars formed from gas, enriched by just one population 3 supernova. These ancient survivors carry chemical fingerprints of the first stellar generation. By analyzing their composition, astronomers reconstruct what population 3 stars created. The ratios of elements reveal core temperatures, explosion energies, stellar masses. JWST searches for direct evidence of population 3 stars. The telescope targets the most distant galaxies, looking for chemical signatures indicating pristine stellar populations. Light from these galaxies shows us the earliest epochs when population 3 stars might still have been forming. So far, no confirmed detection. Every galaxy observed shows some heavy element enrichment, indicating at least a few stellar generations already passed. Population 3 stars, if they exist in observed galaxies, are mixed with later generations, their signatures diluted. But one possibility excites researchers. Maybe some high-red shift galaxies caught by JWST contain ongoing population 3 formation. If pristine gas clouds still exist in isolated pockets, new population 3 stars could ignite even in the modern universe. Finding an active population 3 star would revolutionize astrophysics. We could study its spectrum directly, measure its properties, test models that have remained theoretical for decades. The discovery would be comparable to finding a living dinosaur. The search continues in every deep field. Statistical analysis might reveal population 3 signatures even if individual stars cannot be resolved. Averaged light from entire galaxies could show the characteristic spectrum of pristine stellar populations. Some researchers propose population 3 stars triggered galaxy formation. Their intense radiation and explosive deaths shaped surrounding gas, compressing clouds that would later collapse into galaxies. Without population 3 stars clearing the way, galaxy formation might have proceeded differently. The first stars were universe changes. They ended the cosmic dark ages. They created the first heavy elements. They ionized space. They may have seeded galaxy formation. Everything that followed depended on their brief, brilliant existence, and we have never seen one. That 50,000-degree surface temperature remains theoretical, calculated from models, but never observed. The 100 to 1,000 mass range remains estimated, inferred, but not measured. Population 3 stars exist in equations and simulations. Ghostly mathematical constructs, JWST offers the first real chance to find them. If any population 3 stars still form, if any signatures remain detectable, Webb's infrared sensitivity and spectroscopic precision give it the best shot at detection. Every deep field carries that possibility, and someday perhaps a spectrum will come back, showing the unmistakable signature of pristine stellar fusion. One fraction of a second after the Big Bang, something extraordinary happened. The universe exploded in size, doubling every tiny fraction of a second. Space expanded faster than anything before or since. In less than 1 second, the entire observable universe inflated from smaller than an atom to perhaps the size of a grapefruit. This is cosmic inflation. It sounds impossible. How can space expand faster than light? The same way it expands faster than light today, just enormously more so. Space itself has no speed limit. During inflation, expansion rates exceeded light speed by incomprehensible factors. Why did inflation happen? The leading theory involves a quantum field called the inflaton. This field sat in a high-energy state immediately after the Big Bang. High-energy states are unstable. The field wanted to decay to lower energy like a ball rolling downhill, but instead of rolling, it inflated space. The inflaton field's energy drove exponential expansion. Space ballooned outward at accelerating rates. Then suddenly the field decayed. Energy released by decay reheated the universe, creating the hot, dense state we associate with the early Big Bang. Inflation ended. Normal expansion took over. The entire episode lasted perhaps 10 to 32 seconds. A decimal point followed by 31 zeros and a 1. In that incomprehensibly brief moment, inflation solved several major cosmological problems. First, the horizon problem. The universe appears remarkably uniform in all directions. Temperature variations are tiny, less than 1 part in 100,000. But regions on opposite sides of the sky should have never been in contact. Light has not had time since the Big Bang to cross between them. How do they know to have the same temperature? Inflation solves this. Before inflation, all observable regions were close together in thermal contact. They reached equilibrium. Then inflation stretched them apart faster than light could travel. Now they appear separated, but they remember their common origin. Second, the flatness problem. The universe appears spatially flat. Geometry measurements show space does not curve detectably. But flat geometry is unstable. Any tiny deviation from perfect flatness grows rapidly. For the universe to be flat today, it must have been extraordinarily flat initially. Inflation explains this. Rapid expansion smooths out any curvature. Imagine drawing a triangle on a balloon. Curve is obvious. Now inflate the balloon to enormous size. The surface becomes locally flat. Inflation did this to the universe. Third and most important for galaxy formation. Inflation explains where structure came from. Before inflation, the universe was smooth, but not perfectly smooth. Quantum uncertainty created tiny fluctuations in energy density, regions slightly denser than average, regions slightly less dense. These fluctuations existed at microscopic scales. Inflation stretched them. A quantum fluctuation smaller than an atom got inflated to cosmic size. What began as tiny quantum uncertainty became a macroscopic density variation. These variations survived inflation, persisted through the hot Big Bang phase, and eventually grew into galaxies. Every galaxy traces back to a quantum fluctuation during inflation. The pattern of galaxies across the sky maps quantum uncertainty from 10 to the 32 seconds after creation. Structure at the largest scales reflects physics at the smallest scales. It is a direct connection between quantum mechanics and cosmology. JWST observations test inflation predictions. The theory predicts specific patterns in how galaxies cluster. Certain scales should show more clustering, others less. The predictions are precise, quantitative, testable. So far, observations match predictions remarkably well. The cosmic microwave background shows temperature fluctuations at exactly the pattern inflation predicts. Galaxy distributions match expected clustering. Large-scale structure follows predicted geometry, but small discrepancies exist. Some measurements suggest slightly more clustering than inflation predicts. Others hint at unexpected correlations between widely separated regions. These anomalies are small, possibly statistical flukes, or they might indicate inflation theory needs refinement. Multiple inflation models exist. Some propose one inflated field, others multiple fields. Some suggest slow-roll inflation where the field decays gradually. Others propose chaotic inflation with random field values. Different models make different predictions. JWST helps distinguish between models by measuring galaxy formation timelines, chemical evolution speeds, and large-scale structure patterns. The telescope provides data that favor some inflation models over others. Precision observations constrain theoretical possibilities. One key test involves primordial gravitational waves. Inflation should have generated gravitational waves, ripples in space-time from the rapid expansion. These waves would leave imprints on the cosmic microwave background. Detection would confirm inflation directly. So far, no confirmed detection exists. Current instruments lack the sensitivity to see the predicted signal. Future observatories might detect them, providing the smoking gun evidence for inflation. JWST contributes indirectly by mapping matter distribution that constrains what gravitational wave patterns to expect. The strangest implication of inflation is what it suggests about reality's extent. If inflation happened here, it probably happened everywhere. Space beyond our cosmic horizon likely also inflated. That means the universe is vastly larger than the observable portion, maybe infinite. Inflation might even be eternal. Some regions could still be inflating now, creating pocket universes separated by eternally inflating space. Our observable universe would be one pocket among countless others. This multiverse scenario emerges naturally from inflation mathematics. Testing multiverse ideas is nearly impossible. We cannot observe other pocket universes. They lie beyond our cosmic horizon, forever inaccessible. The concept remains speculative, more philosophy than science, but inflation itself is testable and tested. It makes predictions. Observations match predictions. The theory survives every challenge so far. That quantum fluctuations became galaxies is not just speculation. It is the best explanation we have for observed reality, and JWST continues to test it with every deep field image captured. The Hercules Corona Borealis Great Wall defies comfortable intuition about structure size. This chain of galaxy clusters stretches 1.3 billion light-year across space. To cross it at light speed requires more time than complex life has existed on Earth. The structure is so large that light from one end traveling toward the other end would require over 1 billion years to arrive. Nothing in cosmology predicted structures this massive. Standard models suggest gravity cannot organize matter across such distances. Expansion should pull things apart before gravity can bind them together. Yet there it sits, mapped by galaxy surveys, confirmed by redshift measurements. The Great Wall is not solid. It consists of galaxy clusters connected by filaments with voids between. Think of a pearl necklace stretched across cosmic distance. Each pearl is a cluster containing thousands of galaxies. thread connecting the pearls is a filament of gas and dark matter. But even accounting for emptiness, the sheer extent is staggering. Building something this large requires billions of years of matter flowing toward overdense regions. Gravity must pull galaxies from surrounding areas, concentrating them into the wall structure. The process operates against cosmic expansion, which tries to disperse everything. That gravity, one and all, is remarkable. The Great Wall sits about 10 billion light-years away. Light from it began traveling when the universe was only about 3 billion years old. At that time, the structure already existed, already extended over 1 billion light-years. Formation must have begun even earlier. Initial density fluctuations from inflation seeded the structure. Regions along the wall's future path had slightly higher density from the beginning. As the universe evolved, those regions attracted more matter. Small overdensities grew into large ones. By 3 billion years after the Big Bang, the wall had assembled. This rapid formation timeline challenges simulations. Computer models can produce walls, but usually require more time. Finding one this large, this early, suggests either our initial conditions were more irregular than assumed, or structure formation operated more efficiently than calculated. JWST cannot observe the Great Wall directly. The structure is too large to fit in any reasonable field of view. But the telescope observes galaxies within the wall, studying their properties, measuring their distances, confirming the structure's reality. What makes the Great Wall significant is what it implies about initial conditions. For such a large structure to form, the corresponding density fluctuation from inflation must have been enormous. Not just a small quantum uncertainty, but a substantial variation in energy density across a vast region. Finding structures this large constrains inflation models. Some models predict only small fluctuations, others allow for occasional large ones. The existence of the Great Wall favors models that permit significant large-scale variations. Too many such structures would conflict with cosmic microwave background observations, which show remarkable uniformity. The Great Wall might be a statistical outlier. In a large enough universe, rare events happen somewhere. If inflation created mostly small fluctuations with occasional large ones, the Great Wall could be one of the rare, large examples. We notice it because it exists in our observable region. Other observable regions might lack similar structures. This is fine statistically. Rare events cluster randomly. Some regions get many, some get few, most get none. We happen to see one because our observable patch is large enough to contain rare examples. But if surveys find multiple Great Walls, rarity cannot explain them all. Several large structures have been identified. The Sloan Great Wall stretches 1.44 billion light-year. The South Pole Wall extends 1.3 billion light-year. These are separate structures, independent formations. Finding 3 or 4 suggests they are not that rare. This creates tension with inflation models that predict only small fluctuations. If large structures are common, initial fluctuations must have been larger than standard inflation suggests. Either inflation theory needs modification or our statistical understanding is wrong. JWST's contribution comes from precise distance measurements. Previous surveys estimated distances from galaxy colors and brightnesses, introducing uncertainty. Webb spectroscopy provides exact red shifts, confirming which galaxies belong to which structure. This sharpens our map of large-scale organization. The Great Wall also affects local motion. Its enormous mass creates gravitational pull affecting galaxies hundreds of millions of light-years away. Our own galaxy feels distant tugs from multiple large structures. These tugs contribute to our peculiar velocity, motion independent of cosmic expansion. Mapping structures like the Great Wall helps correct for these motions. When measuring cosmic expansion, we must account for local gravitational effects. Knowing where massive structures sit and how much they pull lets us subtract their influence from our measurements. this improves expansion rate calculations. Every improvement to the expansion rate measurement helps resolve the Hubble tension. The Great Wall might contribute to measurement discrepancies if its mass is larger than estimated. More mass means stronger gravitational pull, means greater corrections needed for expansion calculations. As JWST surveys more galaxies along the wall, mass estimates improve. Better mass estimates lead to better correction factors, lead to more accurate expansion measurements. The chain of refinement continues, each observation slightly improving our cosmic understanding. But the Great Wall's existence alone is the real puzzle. How does gravity build something this large? Why does expansion not tear it apart? The balance between attractive gravity and repulsive dark energy creates these structures, but the exact mechanism remains partially mysterious. And this is just one structure among many scattered across the observable universe. Everything you see in the night sky belongs to the local group. This collection of about 80 galaxies includes the Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies. The entire group spans about 10 million light-year across. It seems vast until you zoom out. The local group is nothing. We sit on the outskirts of the Virgo supercluster, recently renamed Lania. This structure extends 520 million light-years across, containing 100,000 galaxies, organized into hundreds of smaller groups and clusters. Our local group is one tiny association among hundreds. Lania's defining feature is not just proximity, it is gravitational flow. All matter within the supercluster flows toward the gravitational center, a region called the Great Attractor. Galaxies throughout Lania are being pulled inward, though cosmic expansion fights against this motion. We are falling toward the Great Attractor right now. The Milky Way moves through space at about 1,400,000 mph. Part of that motion comes from our orbit around the Virgo cluster center. Part comes from the Virgo cluster's motion toward the Great Attractor. Everything connects in a hierarchy of gravitational attraction. The Great Attractor itself is not a single object. It is a concentration of matter, multiple galaxy clusters merging together. The Norma cluster sits at its core, but dozens of other clusters contribute to its mass. Combined gravity from all these structures creates a deep gravitational well pulling matter from 500 million light-years away. But the Great Attractor is not the final destination. Beyond it lies the Shapley concentration, even more massive, pulling both us and the Great Attractor toward it. The hierarchy extends outward, each level of structure moving under the influence of larger, more distant structures. Mapping Lania required decades of distance measurements. Astronomers measured galaxy velocities using redshift. They separated expansion motion from peculiar velocity by mapping which galaxies move toward which gravitational centers. They defined supercluster boundaries. The boundary is not sharp. Superclusters blend into each other. Defining where Lania ends and the next supercluster begins is somewhat arbitrary. The accepted boundary marks where flow reverses, where galaxies stop falling toward the Great Attractor and start falling toward some other concentration. JWST helps refine these maps by providing better distance measurements to distant galaxies. Knowing exact distances improves velocity calculations. Better velocities reveal flow patterns more clearly. The supercluster structure sharpens with each new data point. What makes Lania humbling is its scale compared to human perception. The entire history of human civilization is a blink in the time it takes light to cross Lania. Every war, every empire, every invention, all of it happened while photons crawled less than 1% of the way across our local supercluster. And Lania itself is just one supercluster among millions. The observable universe contains about 10 million superclusters similar to or larger than Lania. Each one hosts hundreds of thousands of galaxies. Each galaxy contains billions of stars. The numbers become meaningless beyond a certain point. Our position in Lania affects what we can observe. We sit on the outer edges in a relatively sparse region. Dense clusters like Virgo sit closer to the center. From our vantage point, we look inward toward denser structure and outward toward voids. Different positions would provide different views. A civilization in the Virgo cluster core would be surrounded by bright galaxies in all directions. They would see a much more crowded sky. A civilization in a void would see almost nothing, just a few scattered galaxies in an otherwise empty universe. Our position is moderately privileged, not too dense to be overwhelmed by nearby galaxies, not too sparse to lack observational targets. We occupy a sweet spot where the universe is both observable and interesting. Lania's future is already determined. Cosmic expansion accelerates. Eventually, expansion will overcome the gravitational binding holding the supercluster together. Structures on supercluster scales will slowly dissolve as expansion tears them apart, but this takes hundreds of billions of years. For now, Lania remains bound. Galaxies continue flowing toward the Great Attractor. The Milky Way continues its long fall inward. In a few billion years, we might merge with the Virgo cluster joining the denser central regions, or expansion might win first, halting our infall and reversing it. The exact outcome depends on dark energy's properties, expansion's future acceleration, and local mass distribution. Uncertainties in each parameter produce different long-term predictions. What remains certain is our cosmic address. Earth orbits our stellar home. Our stellar home orbits the Milky Way center. The Milky Way orbits within the local group. The local group falls toward Virgo. Virgo flows toward the Great Attractor. The Great Attractor moves under Shapley's influence. Shapley participates in even larger flows. Each scale nested within larger scales all the way to the observable universe boundary. And beyond that boundary, the pattern presumably continues. A dark band cuts across our view of the cosmos. Look toward the Milky Way's disk in the night sky and you see dust. Thick clouds of gas and particles block visible light from more distant objects. This region, called the zone of avoidance, obscures roughly 20% of the entire sky. We have no idea what lies behind it. Dust absorbs and scatters light. Visible wavelengths cannot penetrate thick enough clouds. For decades, the zone of avoidance represented a blind spot in galaxy surveys. Astronomers mapped the universe in all directions, except this one problematic band. The problem is not total. Infrared light penetrates dust better than visible light. Radio waves pass through dust easily. Modern surveys using infrared and radio telescopes have started mapping the zone of avoidance, revealing galaxies we never knew existed. JWST's infrared capability helps dramatically. The telescope can peer through dust clouds that block visible light completely. Galaxies behind the zone appear in infrared, their light red-shifted and dimmed, but still detectable. Each survey reveals more hidden structure. What makes the zone of avoidance particularly frustrating is what we suspect hides there. The Great Attractor sits partially behind the zone. We know it exists from gravitational effects, from how nearby galaxies move, but we cannot observe it directly. Dust blocks most of the view. Mapping the Great Attractor requires piecing together fragments. Infrared observations catch glimpses. Radio measurements detect hydrogen gas. X-ray telescopes spot hot gas in galaxy clusters. Each wavelength reveals pieces of the puzzle. Combining them creates a partial map, but large regions remain completely unexplored. Particularly dense dust lanes block even infrared light. Only radio waves penetrate, and radio surveys lack the resolution to map individual galaxies clearly. We know matter exists there because gravity reveals its presence. We just cannot see what form that matter takes. The zone might hide entire galaxy clusters we have not discovered. If a massive cluster sits behind thick dust, We would not detect it with visible or infrared telescopes. We might eventually notice its gravitational effects on surrounding structures, but direct observation would remain impossible. This creates systematic bias in galaxy surveys. When we count galaxies across the sky, we systematically undercount in the zone of avoidance. This affects statistics about galaxy distribution, large-scale structure, supercluster boundaries. Any analysis that assumes uniform sky coverage produces errors. Correcting for the zone is difficult. We can estimate how many galaxies should exist based on visible regions, then extrapolate to hidden regions. But extrapolation assumes hidden regions resemble visible ones. If something unusual sits behind the zone, extrapolation fails. The Shapley concentration's full extent might be larger than measured. Part of it extends into the zone of avoidance. We map the visible portion, estimate the hidden portion, and calculate total mass. If the hidden portion is more massive than estimated, total mass is underestimated. This affects peculiar velocity calculations. If Shapley is more massive than we think, its gravitational pull is stronger. Our motion toward it should be faster. Corrections to expansion measurements should be larger. The Hubble tension might partly result from underestimated zone of avoidance structures. JWST cannot solve the problem completely. Even infrared light cannot penetrate the densest dust clouds. The most obscured regions remain hidden, but every deep field pointing near the zone of avoidance reveals new galaxies, adding to our partial map. Some discoveries surprise researchers. Galaxies thought to be distant sometimes turn out to sit behind the zone, much closer than assumed. Redeeming from dust mimics cosmological red shift. Only spectroscopy distinguishes dust reening from expansion red shift. This happened with the Great Attractor itself. Early observations suggested it might be a single massive galaxy cluster. Infrared and X-ray surveys revealed it is actually multiple clusters merging together. The true structure only emerged once dust was accounted for. Other structures likely await discovery. Maybe a second greater attractor scale concentration hides behind the zone. Maybe multiple smaller clusters exist there. Maybe nothing unusual exists and the hidden region matches visible regions statistically. We will not know until better surveys complete. Future telescopes might penetrate deeper. Improved infrared detectors could see through denser dust. Radio interferometers might achieve resolution rivaling optical surveys. Gradually, the zone of avoidance will yield its secrets, but some regions might remain forever obscured. The densest dust clouds, the thickest lanes, might block all electromagnetic radiation. If so, we would need gravitational wave observatories or neutrino detectors to map what lies behind them. Gravity and neutrinos pass through dust without scattering. For now, 20% of the sky remains partially unknown, a cosmic blind spot where we cannot see clearly, where hidden structures affect our motion without revealing themselves, where the universe keeps secrets behind a curtain of dust. And every time JWST peers through a dusty region, the curtain lifts slightly.